Hello, everyone, and welcome. Thank you for joining our session, Evolution of the ARM Confidential Compute Architecture and How ARM is Supporting Ecosystem Developers. We're really happy to be speaking to you today. Very happy. We are live from ARM's headquarters here in Cambridge, UK. So let me start by introducing the speakers. My name is Paul Howard. I'm a Principal System Solutions Architect with ARM, and I'm delighted to be joined today by two of my colleagues, Gareth Stockwell, who's a Senior Principal Systems Architect, and Nicholas Sample, who's a Senior Manager for our education engagements. Our session today is in two parts. In the first part of the presentation, Gareth is going to take us through the evolution of the ARM CCA platform. So he's going to give us an overview of the architecture and its components, and he'll be talking about the technical roadmap and describing the features that are being added incrementally in firmware. And then in the second part of the presentation, Nicholas and I will talk about how we want to support and engage with developers in the ecosystem so that this technology is ready to be successfully deployed as soon as CCA-enabled systems start to become available. So at this point, let me hand over to Gareth, who is going to lead us through the first part of the session.
Thanks very much, Paul. Thanks. So, as Paul said, we'll start with some information on what ARM is doing to evolve the CCA offering. But just before we get to that, I wanted to set the scene by giving an overview of CCA as it stands today. So the ARM solution for confidential computing comprises two parts. The first part is the hardware architecture extensions, which we call the Realm Management Extensions, or RME. These extensions provide the necessary primitives for the construction of hardware-based confidential compute environments. And these primitives include isolation, dynamic resource management, and attestation. The word realm, by the way, as we'll see in later slides, is simply ARM's name for a confidential VM. RME was added to the ARM architecture in v9.2. Then sitting on top of RME exists a software stack. And the combination of that software stack together with the RME-enabled hardware is the entire solution that we refer to as CCA, the Confidential Compute Architecture. The software stack exists both within and also extends beyond the device. So the software stack within the device includes enablement, which is added to the trusted firmware components and also to Linux KVM. And together, that enablement allows the creation, the management, and the scheduling and execution of realms. Outside the device, the stack extends to include components which provide support for endorsement and attestation of confidential compute platforms. And Paul will give some more details, particularly on those latter topics later on in this presentation. So let's look first of all at how an ARM software stack, an ARM system looks before the advent of CCA. So this slide shows the software components which could be found on a typical ARM server platform. And just like other architectures, the ARM A profile allows software to run at different levels of privilege. These are referred to in ARM as exception levels, and they're numbered from low to high privilege. Additionally, the ARM A profile has the concept of security states. And since back in ARM v7, Trust Zone has supported exactly two of these states, otherwise known as worlds. And those two are secure and non-secure. This separation allows functionalities such as platform power management to be isolated and protected from the main operating system, with context switching between the two security states managed by a monitor running at the highest exception level, the highest privilege level, EL3. Each of those two security states has its own physical address space, so regardless of what the OS or the hypervisor writes into its own translation tables, how it uses its own memory management architecture, it isn't capable of mapping memory which is owned by the secure world. So we build on these primitives, we build on these patterns moving forward into CCA. And so with the advent of CCA, and in particular with the advent of the Realm Management Extension, the platform looks something like this. RME introduces a new security state alongside the non-secure and secure states called Realm. This new security state has its own associated physical address space. And just like the secure world, the Realm world is protected against access from the non-secure world. Furthermore, in order to maintain and allow mutual distrust between Realm and secure worlds, RME also introduces a fourth world, which we call root, and that contains the monitor that performs switching between the other three worlds. Within the Realm world, CCA introduces a new firmware component called the Realm Management Monitor, or the RMM, that executes at exception level 2 in Realm security state. And the roles of the RMM are twofold. Firstly, it enacts policy defined by the hypervisor for resource management and for scheduling. So the RMM itself doesn't make policy decisions, it doesn't make scheduling decisions, but it enacts those decisions that have been made by the hypervisor and communicated to it. Secondly, the RMM enforces the security constraints which are required and relied upon by the confidential compute guest, by the Realm. And ARM publishes a specification for the RMM, which defines two interfaces, as shown on the diagram here. One is the Realm Management Interface, the RMI, and that's used by the hypervisor to create, manage, and run realms. The other interface, the RSI, or Realm Services Interface, is exposed to the Realm guest and provides functionality including attestation primitives and mechanisms for communicating with the non-secure world. So what is the status of CCA today? There is a wealth of resources available publicly from ARM. They're shown on this slide. These underlined text are hyperlinks, so hopefully in the slides that will be distributed, they'll be available to you. But all of these links are reachable via developer.arm.com. So the resources include the hardware architecture specs, both at the system and the CPU levels. Also fixed virtual platform simulators, which come in two flavors. There's a base architecture, FVP, which aims to simulate the widest possible set of architecture features. And then there's a Fremont reference design, FVP, which simulates a hardware system that targets the infrastructure segment. And that's where we expect to see the first ARM CCA deployments. The RMM spec that I mentioned previously defines interfaces exposed to the hypervisor into realms. And then there are reference implementations of components, including the RMM, which are hosted in the Trusted Firmware project. And finally, on this slide, there are a set of learning resources which show how to use CCA in real-world solutions, in real-world scenarios. And Nick and Paul will speak more about those later on. So let's move on to what ARM is doing to evolve and develop ARM CCA. All the resources that were on the previous page provide the foundations for ARM CCA. And specifically, they allow the work to begin on taking existing workloads, which are running on CPUs in non-confidential VMs, and migrating those workloads into realms. So that work can begin today and is ongoing. However, in order to reach the goal of CCA being as widely deployed as possible, for example, one possible goal is that each and every workload in a public cloud migrates into an ARM CCA realm. Then to realize that goal, there's more work to do. And the next few slides will provide an outline of what ARM is doing to take ARM CCA to that next step. So when we present CCA to our partners and discuss it with other groups in the ecosystem, the feedback we hear can be summarized in three categories, and they're listed here. So firstly, from a security standpoint, in addition to the isolation barriers which ARM CCA provides, partners are also looking for additional protections to enable defense in depth. Secondly, when thinking about migrating workloads into realms, naturally, the users of those workloads want to be able to leverage the same set of platform features, use the same set of computing capabilities, and attain the same levels of performance as they can already get in non-confidential VMs. So we're aiming to provide feature parity between realms and non-confidential VMs. Finally, service providers in the infrastructure space in particular are constantly looking to extract the highest possible levels of reliability, availability, and serviceability. And ARM's working hard to enable this, again, including platforms which host realms. So to address all these requests, we're working on enhancements to the RMM spec and to the reference software stack. And that's what I'll talk through in the next few slides. So first, let's look at one of the extensions which ARM is adding in order to strengthen the security guarantees which realm owners can benefit from. So RME is fundamentally an isolation architecture, which provides strong access controls in two ways. Firstly, between realms, access controls are enforced via translation tables, which are managed by the RMM. And then between worlds, access controls are enforced by the hardware. And this diagram shows how physical memory is managed on an RME system. Each granule of memory, and when we speak of granules, we typically talk about a chunk of memory of 4 kilobytes in size. each granule of memory is accessible in one or more physical address spaces. So on this diagram, we have a set of granules of physical DRAM, which can be accessible in either realm or non-secure paths. And the set of those physical address spaces can therefore be seen as aliased views onto a common underlying physical resource, in this case, DRAM. Accessibility of those physical resources in each physical address space is controlled by software running at EL3 at the highest privilege level. And at boot, that software configures the hardware such that most of DRAM is available exclusively via the non-secure physical address space. And then there's a small amount which is carved out for use by other worlds. So on this diagram, we're showing that at boot, there's an RMM carve out for the RMM's code and data. Optionally, the platform can then provide additional protection by encrypting memory contents, physical memory contents on a per world basis. And this diagram down at the bottom shows that memory which is accessible via realm physical address space is protected with a realm worldwide key. Now, when realms are created, their memory contents are protected too with the same realm worldwide key. And as I said before, this protection is in addition to the access controls provided by the combination of RME and the RMM's translation tables. But partners have told us that they require stronger protection at the physical memory level. So to address that need, we're introducing an extension to the hardware architecture called memory encryption contexts. And this allows the memory encryption key or tweak to be programmed to be configured on a per granule basis. And so the RMM can then make use of this extension to protect the contents of each realm with a separate key, and then to use a further separate key to protect its own memory contents. So taken together, this allows the service provider to promise their tenant that the tenant's data is uniquely protected all the way through its lifetime, including when stored in memory. Moving on then to some of the features we're adding to provide feature parity between realms and non-confidential VMs, and therefore smooth the migration path. The first of these features is concerned with enabling privilege separation between multiple software components within a realm. So if we start with a very simple in-realm software stack depicted on this diagram, the workload is a combination of user space components and a kernel. RME and CCA provides an isolation boundary, namely the realm, such that that workload is isolated and protected from the untrusted hypervisor, which is not shown on this diagram. The problem is that the kernel typically relies on some runtime services. For example, these might include a TPM, which the kernel uses for secure boot, key provisioning, or attestation. Or alternatively, it might include variable storage, which is used by the in-VM guest firmware. And if this workload was running on a bare metal platform, then these services would be provided by a mixture of hardware and firmware. In a typical traditional VM, some of these services could be emulated by the hypervisor, but clearly that's not a solution which we can use for realms, as that would violate the confidential compute security model. So we need to find a way to migrate these services into the realm itself. And simply moving those services into the guest doesn't work or doesn't provide the necessary isolation and protection, because the services may be provided by a different vendor from the guest OS image, so that may provide barriers to integrating them with the workload. And more critically, these services need to be protected from the guest OS. So therefore, we need a mechanism which provides isolation and privilege separation within the realm. And the proposed solution for this in ARM CCA is called planes, which works like this. At realm creation time, the configuration parameters which the non-secure hypervisor provides includes a desired number of planes. So in this example, 2. And each plane is effectively a separate VM with its own kernel, its own user space. But all those planes execute together in a common guest physical address space. Each vCPU within that realm, of which there can be multiple vCPUs, executes in a single plane at a time, and there's banked register state per plane. And then we nominate one special plane, the 0th plane, shown on this diagram as the paravisor, which manages switching between the other planes, can restrict memory access permissions observed by those other planes, and can also emulate functionality such as interrupt controllers. So all this means that the hypervisor can continue treating the realm as a single opaque unit of compute, assigning resources to that unit of compute, such as CPU cycles and memory. And then within the realm, we have this privilege separation boundary, which allows functionality to be protected from the guest OS and provide services towards that guest OS. The other feature that we're working on to smooth migration of existing workloads into realms is enablement of direct device assignment to realms. And before we get into the details of how that works in CCA, first there are some key questions that we need to ask ourselves. So if we're assigning an I/O device or an accelerator to a realm, then those questions would include: what is the identity and configuration of this device? And are those something which I, as the realm owner, am willing to trust? Similarly, which firmware is the device running? And again, is that a trusty firmware version? Regarding memory access from the device to the realm's memory, have the I/O MMU mappings which allow that access been set up correctly? When the realm communicates with the device through the system fabric, is that communication adequately protected as it passes through the system? And finally, when the realm has been using a device and therefore potentially causing confidential state to be stored inside that device, is there a guarantee that that state will be scrubbed when the device is reassigned to another realm or VM? So for PCIe devices, there are a set of standards which we can build upon to provide the required guarantees. And two of those key standards are shown on this slide here. So the first is the Trusted Device Interface Security Protocol, or TDISP. And that defines a reference architecture that describes the components of a system and the trust relationships that exist between them. It then describes ways in which the trusted VM or realm in CCA terminology can attest the identity and configuration of a device function. And finally, it defines a state machine, which allows separation between the operations performed by the untrusted host hypervisor, for example, configuring the device, programming its bar addresses and so forth, and the assignment of that function to a confidential VM. And it's that state machine that includes the notion of scrubbing, which will be ensured before the device is reassigned. Another key standard that we're building on is IDE, Integrity and Data Encryption, and that provides the necessary physical link protection between the host SoC and the device. And so the work that ARM's doing includes mapping of the TDISP reference architecture onto the corresponding components of CCA, and also extending the RMM ABIs so that they comprehend the concept of device assignment and provide the functionality that allows the hypervisor to assign device functions to realms and allows realms to attest and establish trust in those device functions. We're also working with companies across the industry to make sure that the device assignment solutions that we come up with and also those provided and proposed by other architectures can fit together into a common software framework within contemporary operating systems. At the hardware level, ARM is also defining and extending other standards which are important to the device assignment feature, and these complement those from PCI SIG. They allow IP vendors, which are implementing ARM architecture, to provide products which can be easily integrated into confidential compute solutions. And so two key standards that are currently or have recently already been extended are the ARM System MMU architecture, which has been extended to add awareness of realm world, and that provides an interface which allows the RMM to manage the address translation used by realm assigned devices. And the RME system architecture has also been extended to add guidance for vendors of components such as PCIe root ports. So let's move on to the third area where we are evolving and developing CCA, and that's enabling service providers to maintain their systems while still providing the high availability service demanded by confidential compute guests. So cloud service providers periodically need to deploy updates or patches to firmware or software components which are running on their systems to fix bugs, to improve performance, for example. And so let's consider the example of an update to the RMM. If that RMM is actively servicing running realms, then one option would be simply to, before applying the update, to require that those running realms are brought down. The update can then be applied, and then once the update has been deployed to the system, the realms can then the workloads can then be reinstated. However, clouds naturally aim to attract business by offering high availability, and so this model really isn't attractive to cloud service providers. So we need to look for alternatives, and there are two models that we're currently exploring. So the first of those is to migrate the workload onto a different server. So in this example, the server on the right already has the new firmware image, the new firmware update installed. And so the workload can be migrated from the machine on the left across to a comparable machine on the right. And that allows the first machine then to be serviced. An alternative is to allow firmware to be updated while the workload and its state remains live in memory. So in this model, the realm would first be paused for as small a time period as possible. And while that realm is paused for the critical period of the installation, the update is applied, and then the realm is unpaused and allowed to continue running, now on top of the newly updated RMM. And so comparing those two mechanisms, the migration mechanism and the live update of firmware mechanism, while those two are clearly very different, there are many similarities, particularly from the point of view of realm attestation. And in each case, the TCB of the realm changes dynamically while the realm itself continues to run. From the guest point of view, that update is transparent, but it clearly needs to be reflected to the realm owner or the relying party via attestation. And that relying party needs to be able to attest not only the current TCB that the realm is running on, but also the entire history of TCB versions which that workload has been exposed to. So as I said, ARM is exploring each of these two options, each of these two models, and developing and proposing ABIs and data structures to enable them. So in summary, therefore, ARM's busy adding lots of new features to CCA in response to what we've heard from the ecosystem, and we'll continue to listen. But meanwhile, I'll hand over to Nick, who will tell us about how ARM is supporting that ecosystem and making best use of CCA.
Thanks, Gareth. I think we've got a bit of a problem with the video stream, so I'm not sure that you can see us. We hope we'll get that back up and running for the live Q&A, which starts in just over half an hour. But hopefully you can hear us clearly. So Gareth touched on the materials that are available from ARM, including reference resources and specifications. Paul and myself, we'd now like to turn our attention to the range of support for developers working with confidential compute, which ARM is currently rolling out. So I would like to talk about the different types of support we offer to developers. Paul will then touch on the kinds of learning experiences we are looking to develop connected with confidential compute, before we then ask for your feedback. So we're hoping this is a live feedback session where you can provide us with your ideas and thoughts within the chat, or provide us some comments in a feedback form, which we'll provide a link to within this session. So what kind of materials does ARM provide to support developers? Well, if you visit arm.com/developer hub, you will see a range of content, including training, tutorials, videos, and also a link to a vibrant community of developers, thousands of developers, where it includes a forum, a chat function, where you can share your ideas and support each other and request support from ARM experts and experts within the wider community. We also develop what we call learning paths. And learning paths are bite-sized training content which support you in key tasks and workflows. And you can see those learning paths if you visit learn.arm.com. And what can you expect to find within the learning paths? Well, here's an example. So get started with realm management extension. Each learning path follows a similar format. It begins with a clear definition of the audience that the learning path is intended for. It describes what is covered within the learning path, and this one here is 30 minutes long. That's fairly typical. And it also describes in detail the prerequisite skills and knowledge that you need in order to be able to engage with the content. So you will find on learn.arm.com already 3 learning paths connected with RME. There's Get Started with Realm Management Extension, which I showed in the screenshot on the previous slide. There is also a learning path where you can learn to create a virtual machine in a realm and also run an application in a realm. And there are more to follow. So what we would like to do is to get your feedback on our ideas so far. What skills or workflows connected with confidential compute would you like guidance on? Now, there's a QR code here, which if you select it, will take you to a short feedback form, just 6 questions long, very quick to complete. We will bring this up again at the end of the presentation. So as Paul is talking through our plans so far, we'd love you to reflect on the kind of support that you would like to see from us, and to give us some feedback, give us some pointers as to the what you would like us to prepare in terms of training content. So I'll now hand over to Paul, who will give you an insight into how we're creating these learning experiences, and then we'll move on to the Q&A session.
Okay, thanks very much, Nick. So yes, in this last part of the presentation, I will cover some more details about the kinds of learning experiences that we want to create for developers, so allowing you to get hands-on with the ARM CCA technology. And I want to frame this in terms of building blocks and patterns. So over time, the learning path content for CCA will evolve to demonstrate different use cases and different facets of the technology, which will be of interest to different audiences, depending on what they want to learn or what they are trying to achieve. But these different demonstrations and tutorials will have some things in common. They will have some technical components in common, of course, and these are our building blocks. But they will also have common patterns of interaction between those components as well. So in this section, I'm going to introduce the CCA reference stack itself, which is a convenient and self-contained package for running realms in a software emulated environment, which is available today. I'm then going to talk about how that reference stack fits into a framework for common workflows, which will pave the way for demonstrating how realms can typically interact with other components and services. Now, early on, many of these typical interactions will be related to attestation. So I'll end by talking about how that common workflow framework can be applied to attestation flows and patterns. So let's begin here with what we call the CCA reference stack. The reference stack is a functional implementation of everything that you need to run confidential virtual machines on ARM. The reference stack is based on Linux, it's based on KVM, and it's based on components from the open source Trusted Firmware project. Trusted Firmware provides the secure monitor that runs in the most privileged mode of the CPU. It also provides the realm management monitor, the RMM, which is the component that works in combination with the hypervisor to manage the lifecycle of realms, so that the hypervisor itself can remain untrusted. The hypervisor in the reference stack happens to be KVM, and then Linux is the operating system that runs both on the untrusted host and also within the realms, where it takes on the role of the guest operating system for those confidential virtual machines. This is the CCA reference stack. CCA requires the hardware extensions that include RME, the realm management extensions. Hardware with RME is not available just yet, so the package includes an instance of the FVP software model, which Gareth talked about in the first part of the presentation. FVP, to remind you, is the fixed virtual platform, which is a simulation of the ARM architecture that can be used to get access to new features of the architecture in advance of the silicon. The FVP provides that baseline enablement that is then foundational to everything else. For convenience and simplicity, we provide this entire stack within a single Docker image. This means that it can run on any suitable development machine that has Docker installed. There's no dependency on the hardware because everything runs in a software model. Our learning paths will show you how to obtain this container and start running the components of the stack. With the reference stack, we can run Linux-based confidential virtual machines. And within those confidential virtual machines, we can run applications. That's the black box in the diagram. The demo application can be anything. A simple Hello World application example is provided in the learning path materials. You can bring your own application to this system, and the resources in the learning path will help you to build it and get it running. So that's the reference stack. This is the first building block, if you like, from which we can start to create the convenient and informative developer experiences for our learning path resources. The next thing I want to explore is this idea of a framework for common workflows. And this means adding more building blocks. What do I mean by common workflows? Well, I'm talking about the patterns that tend to recur wherever confidential computing happens. And by far the most ubiquitous of these patterns is attestation. Attestation is a defining characteristic of confidential computing. A confidential environment must be able to prove itself as such. And there are common architectural patterns that lend themselves to implementing these proofs. This builds on the reference stack package from the previous slide. Indeed, what you see on the left side of this diagram is just the reference stack. That's our FVP software model supporting confidential Linux guest VMs. We can run applications inside those confidential guests, as we've just seen. But let's suppose now that our application is not simply a hello world, but it's something a little more realistic, a little more illustrative of the needs of a confidential computing deployment. Our application wants to request some kind of secret from the outside source. For instance, a service that is running outside of the confidential guest. Let's call this a secret broker. It could be something like a key management service, for example. If you know the Cocoa Confidential Containers project, this piece could be something like the Cocoa KMS. In order to obtain a secret, the client application must first prove that it is running in a confidential environment where that secret will be adequately protected in use. And so the client application provides attestation evidence to the secret broker. The evidence now needs to be verified. One way that the secret broker can achieve this is by calling out to a separate verifier service. And for this, we connect with the world of community open source projects. Shown here on the right of the diagram, Verizon is an open source project within the Confidential Compute Consortium. Verizon provides reusable components that can be used to build verification services with a high degree of interoperability by making use of standardized data formats. Much like the CCA reference stack, Verizon can also be conveniently deployed in a set of containers, which we can then bring alongside the other components to create this staged landscape showing attestation and verification from end to end. The final piece of the framework emulates a factory provisioning step, which is a simplified model of the hardware and firmware supply chain. This will demonstrate how to create a standard description of a valid CCA platform, a process that's often referred to as endorsement. Verizon has a provisioning service that is capable of ingesting these endorsements, again, in standard data formats, and storing them in its database. These then provide the reference claims, the measurements, and the trust anchors that Verizon needs in order to appraise a piece of attestation evidence coming from the realm. Again, all of these pieces are containerized for convenience, and the containers can share a bridge network to facilitate the remote communication between the components and the services. Everything can still run on a single developer laptop. Now, this is a simple picture, and it's a convenient picture, and deliberately so, but it's also a picture that will evolve over time. Our learning content will not always be restricted to the use of FVP simulators. They will continue to be relevant as we look into future real-world systems where perhaps not everything is staged on a single laptop for experimentation, but perhaps where components are more distributed and scaled out. The topology and the experience might then change, and we will update and extend our learning paths accordingly. But these simple containerized worlds are where we are focused initially. Now, the reason why it's useful to have a reusable template for these attestation flows is that it flexes and adapts itself well to the different points and different contexts in which attestation might take place. So here's a model that I think is useful. We can think of attestation as being a deployment gate. Because attestation is a defining characteristic of confidential computing, it follows that the deployment of a workload needs to halt and wait for some attestation to happen before it can proceed to the next step. So it's a gate, and it's a gate that we can apply at different times. We could apply the gate at boot. So for instance, we could encrypt the entire VM disk and not release the decryption key until an attestation has been successfully verified. Or we might have other boot time secrets that we release only in exchange for a verified attestation, such as the seeds for virtual TPM or UEFI variables. Or maybe we gate something other than boot. So in this case, it might be something like a container image that needs to be decrypted, such as what happens in the confidential containers architecture. If not a container, then it could be some other aspect of the executable workload, such as a WASM module or even a native application binary that's encrypted. And again, the key gets released in exchange for verified attestation. Another time when you might use attestation as a gate is when establishing a secure channel with some service that exists outside of the realm. Secure channels are naturally achieved using TLS, and there are projects that are looking at making attestation an inherent part of the TLS handshake, so that you can't even establish TLS without it. In fact, ARM is contributing to one such proposal within the IETF and building a POC that is an open source project within the Confidential Compute Consortium. But even if you're not using attestation as part of establishing TLS, then you might still have some kind of attestation protocol that goes over the top once TLS is already established. This could be some very application-specific thing, or we might find that common processes and tools emerge. But the end result is the same. The relying party or service that's outside of the realm is going to keep hold of any confidential data or decryption keys until some attestation evidence has been received and verified. Now, clearly, all of these workflows differ in terms of detail and in terms of the sequencing of events. But I hope you can also see that there is also commonality. In all cases, there is an attesting environment running in a realm which provides the evidence. There is a relying party that's going to request that evidence, and there is a verifier that's going to verify it. So all of these flows are well serviced by the common component framework that I showed on the previous slide. It means that we can create targeted learning path experiences to demonstrate these specific use cases, but then we can build on those different experiences using at least some of the same pieces. And over the coming months, we'll be releasing learning path content on learn.arm.com, making use of this common framework and demonstrating these different attestation flows. But as Nick said, we also really want to be steered by our developer communities. We want to provide content that is relevant to you. So let me end by sharing once again this feedback slide. If you're doing work that intersects with confidential computing in any way, on any system, then this questionnaire is an opportunity for you to tell us about it. What are you working on? What challenges are you facing? Perhaps you contribute to an open source project and you have particular gaps to address in order to get it working on ARM CCA. Let us know where we can help, and we can add these things to our future roadmap.